This is the third module based on chapter 3 of your ebook by Chengel. This module will be broken up into parts. This is the first part. The module covers pure substance. In this module, we'll look into the property diagrams, PV, TV, and PT diagrams, PVT diagram, phase diagrams, states of pure substance and its properties, of course the tables in the appendices. What is pure substance? Pure substance is one that is homogeneous in position, 2, homogeneous in chemical composition, and thirdly, it does not change with time. Let's look at an example for a better understanding of a pure substance. We have a closed container filled half with liquid water and half with steam or vapor. So this is a pure substance, although it exists in two phases. Why? Number one, it is homogeneous in position. Anywhere you go in the closed container, you're going to see 2H and 1O. So it's homogeneous in position. And it is homogeneous in chemical composition. Everywhere you go in the tank, you're going to meet with H2O molecule. With time during your analysis, even if some of the liquid water vaporizes or some of the vapor condenses, you're still going to see H2O everywhere, 2H and 1O everywhere. So the closed container of a liquid water and steam is a pure substance. Even if 3/4 of it is liquid or 3/4 of it is vapor, it is still a system of pure substance. Next, how about the closed container of liquid water and ice? It's similar to the above example. How about a solution of salt in water? Would that be called a pure substance? Or a cup full of tea? So in that cup full of tea, your system, is the tea homogeneous in position? Not the cup, it's the tea. Is the tea homogeneous in chemical composition and does not change with time? If it satisfies the 3 criteria, then your cup full of tea contains pure substance. A container of air would be pure substance, even if you know that there are nitrogen, oxygen, and all that rare gases. Unless, of course, a nitrogen and oxygen reacts with each other during your analysis. Then it doesn't satisfy, does not change with time criteria. Here in this thermodynamics analysis, we shall concentrate on simple compressible substance. Simple because magnetic, electric, and surface effects are insignificant. We ignore them. Compressible is because if one of the system properties like temperature or pressure changes, then the volume also changes. That's compressible. Now, if these effects like the magnetic, electric, surface effects are to be considered, then their contributions in some form have to be taken into the analysis. It may involve additional equations, additional property tables. It's quite complex, but it can be done. Yeah. So let's have a look at vapor, liquid, solid phase equilibrium in a pure substance. We consider a system of 1 kilogram of water at 25 degrees C in a frictionless piston cylinder arrangement as given here. We say frictionless, which means that the piston is free to move without resistance. You have water at 0.1 megapascal. As the water is being heated, the temperature increases. The specific volume increases because now the piston is free to move without any resistance. So the pressure is unchanged. It's an isobaric process. Now when the water is further heated, it reaches 99.6 degrees C or about 100. Additional heat transfer will change some of that liquid into vapor. The pressure remains unchanged because the piston is free to move. The temperature remains unchanged, but the specific volume increases because the piston is moving outwards. Okay. We look at the property diagram TV here. You have your water here at 25 degrees C. As you heat it up, and the piston is free to move outward, and finally at 99.6 degrees C or about 100, some of the liquid starts to vaporize. Now if you add more heat, okay, the temperature remains constant and the pressure remains constant, until much more of the liquid vaporizes. If the cylinder is long enough, further heating up of the cylinder will push the state of the your working fluid to reach here until all of it vaporizes. If the piston is stuck somewhere here, not able to move, let's say you put more weight on the piston, let's say somewhere here, and if you add more heat, what's going to happen is that the volume can no longer change because it's stuck there, certain location. The temperature will increase, so will the pressure. So you have an isochoric process here. And you may stop at any particular temperature and pressure. It's a property TV diagram. Saturation temperature is the temperature at which vaporization takes place at a given pressure, saturation pressure. You could say that at 1 atmospheric pressure or 100 kilopascal, the saturation temperature for water is 99.6. That means if you maintain the pressure at 100 kilopascal, the water is going to boil at 99.6 degrees C. Or it's the other way around. You can say that the saturation pressure of water at 99 degrees C is 0.5 megapascal. Which means if you have your water at 99.6 degrees C, the saturation pressure is going to be 0.1 megapascal. So you can look at the another property diagram, the Pt diagram. What you see as a line here, is actually just a point. So as you heat your liquid region here, liquid at 1 atmospheric pressure, further heating up under constant pressure process, and then more and more of your liquid will vaporize until all of it have vaporized, then it falls into the vapor region. Okay. So in thermodynamics analysis, our working fluid is liquid, vapor and gas, no solid. So most of the time we are looking into this region, the liquid region and the vapor region. The point where all the three main phases exist at the same temperature and pressure is called the triple point. Here on this you can see triple point. This is where solid, liquid and vapor exist at that particular state. The phase diagram for water and most other substances are different because specific volume of water increases as it solidifies. Unlike other substances, the specific volume decreases. Why? Because the attractive forces in solids are stronger than in liquid. But water is a special case. Let's have a look at the property diagram here for PV and TV at the lines and the region. Now, the region on the left of this line is called subcooled liquid region or compressed liquid region. It's the same thing. The line itself is saturated liquid line. The region under the dome is saturated liquid vapor region, where you have both saturated liquid and saturated vapor exist. Closer to the left line, we have more liquid than vapor. Closer to this line, we have more vapor than liquid. So the line itself, marked by number 4, is saturated vapor line. And on the right hand side, the region is called superheated vapor region. You have seen this schematic diagram of PV, the property diagrams in module 1 in my lecture earlier. So this is the TV diagram. The only difference is the constant temperature and constant pressure lines as compared to the PV diagram. Okay. Even though solid is not in our working fluid in thermodynamics analysis, just to have a look at where the solid liquid line and the solid vapor line lies. So you can see here for water, and this is for all other substances, most other substances that contracts on freezing. So actually, your PV, your TV, and your PT diagrams were extracted from the three-dimensional PVT diagram. And these PVT diagrams have been obtained experimentally over series of experiments. So if you look at this figure 323 and figure 324 in your ebook, if you look up from the front side here, the P, you're going to see the PV diagram. If you look from the top, you're going to get a TV diagram. If you look at from this side, you're going to get a PT diagram. So actually a complete diagram is the PVT diagram. Okay. This is for water because water expands on freezing. Properties of water is given in the appendix. You can check out A4 up to A7. You'll see that anything with the subscripts F is a specific property of saturated liquid. Subscript G is saturated vapor. And FG, subscript FG means the value of YG minus YF. Y being any property listed in the table. It could be specific volume, specific internal energy U, specific enthalpy. Watch out for the units. Where HFG is the enthalpy of vaporization. It's the latent heat of vaporization. It is the amount of energy needed to vaporize the unit mass of saturated liquid at a given temperature or pressure. An example, instruction of table A4. This is saturated water temperature table. So you see here that any temperature, this is where the water starts to vaporize, the saturated pressure. Let's say if you have water at 20 degrees C, the water will start to vaporize at 2.3392 kilopascal. This is the saturated specific saturated liquid, specific volume. This is internal energy for saturated liquid, internal energy for saturated vapor. This is just UG minus UF. You see, minus this. Okay, and this is enthalpy, lowercase h. We will use this much in our thermodynamics analysis of closed and open systems later. There is also the pressure table, which means that at 20 kilopascal, the water is going to start to vaporize at 60 degrees C. So it's the same columns here. There are also superheated vapor and compressed liquid tables for water. That is for this module.